No, so a little bit different format of the video today because I didn't have access to any space with a whiteboard, and honestly I was kind of lazy to go to a classroom with all my camera gear just to film a short video on rank and dimension, so we're going to talk about what I wrote for today. Yay! So like I said, rank and dimension is the name of the game. So rank is the amount of linearly independent rows of a matrix, so let's consider matrix A being this guy. The rank of this matrix is 1 because you can say that the first row is half of the second row, or vice versa. 2 R2 equals R1, as you see here. Or consider B, however, which is this matrix, which both rows are linearly independent. In this case, both rows are linearly independent, so the rank of B is 2. Now for square matrices, the following is true. If you have A to be an n by n matrix and the rank of A is n, then A is invertible. So this is what we call having full rank of a matrix, and all the theorems and all the other facts about invertibility hold true as well. So if you say that rank of A equals n, then you know that the determinant of A is not equal to 0, the rank of A is equal to n, A is invertible, and so on and so forth. Now let's look at dimension. Dimension is effectively the same thing as a rank, but for a vector space. It is defined by the amount of vectors that form a basis for the given space. In our case, the space is V. So consider the dimension of the row space of A, which is the amount of non-zero rows. Again, as with the above example, in A, the rank of A is the dimension of the row space of A, which is equal to 1, and B, same holds true, but the answer is 2. So from this you could see that the rank of A is equal to the dimension of the row space of A, and we have a couple additional facts here. So here are some facts. If W is a subspace of V, then the dimension of W is less than or equal to the dimension of V, and this is seen by showing W being a smaller subset of V and thus being of a smaller dimension. The space of Rn has a standard basis, so the dimension of Rn is always n. And the dimension of the column space or the row space, the two are actually equal, is equal to the dimension of the null space, which is equal to n for any m by n matrix A. And this also holds true for square matrices. And so that means that the rank of A is equal to the dimension of the null space, which is equal to n, which is the amount of columns. And this is what's known as the rank nullity theorem. Very useful when trying to figure out the dimension of a null space or what the rank is, or figuring out if a matrix is invertible. Because a matrix is invertible if the rank of A equals n, therefore the dimension of the null space must be 0. And that's all for today. Hopefully tomorrow I'll have a better setup for all of this, and we could talk about something else, such as vector spaces, subspaces, maybe determinants. We'll see what we get.